In this lecture, I want to continue our discussion on number systems and base conversion. Number systems and base conversion. Okay, we continue with one example to convert between two bases. We have this number. We have AF dot 16C in base 16 and we want to convert it to base 8. Okay, we have few ways. The first way is to convert from base 16 to base 10 and then from base 10 to base 8. We have another way for base conversions as shortcut, and we said if beta is equal to alpha to the power of k, we can directly convert from base alpha to base beta or base beta to base alpha. Here, base alpha and beta, base alpha is 8 and base beta is 16. So if we look to this equation, we see that we cannot find a relationship between 8 and 16 in a way that we say a to the power of k is equal to 16. So this shortcut is not going to work for these two bases. So the first method which still works is converting from base 16 to base 10 and from base 10 to base 8. But we have another method which is easier than this method, and that method tells us that to convert from base 16 to base 2 and then convert from base 2 to base 8. Okay, this one is easier. Of course, the only thing we need to do for converting from base 16 to base 2 is writing the numbers in binary form. And from that point, we can use the shortcut because for these two bases, we know that 2 to the power of 3 is 8. So we can use the shortcut method. So first, let's write the number in binary form. The number was AF.16C, base 16. We want to write it in base 2. We start from like A. A is 10, 10, 1, 0, 1, 0. F is 1, 1, 1, 1, dot. 1 is 0, 0, 0, 1. 6 is 1. 6 is yes. 6 is 0, 1, 1, 0. Sorry, 6 is 0, 1, 1, 0. And the last one is C, which C is 1, 1, 0, 0. Okay, so how we know that C is 1, 1, 0, 0, A is 1, 0, 1, 0? I will talk about it in a little bit. So first, let's finish this example, and then I will talk about those conversions. Now that we found this number in base 2, it's time to convert from base 2 to base 8 because 2 to the power of 3 is 8. We need to group the digits in a group of 3 and write it in the base 8. So we start from the radix point to the left and the right. So first let's go from radix point to left. So one group, second group, and third group has two members. We add 1 0 to the left side of integer part. From the radix point, this time we move to the right. So group of 3, 1, 2, 3, and 4. Now we write these numbers in base 8. 0, 1, 0, 0, 1, 0, of course, is 2. 1, 0, 1 is 5. 1, 1, 1 is 7. Dot. 0, 0, 0, 0, 0, 0 is 0. 1, 0, 1 is 5. 1, 0, 5, 1 is 5. And 1, 0, 0 is 4. So we can say AF 16C in base 16 is 257.0554 in base 8. Okay. One other example. Let's convert 1023.231 from base 4 to base 5. Okay, the only method that we can use is converting from base 4 to base 10 and from base 10 to base 5. So in order to convert from base 4 to base 10, we multiply each digit with the base with the power of n to convert it to base 10. Let's do that. So we can say 1 times 4 to the power of 3 plus 0 times 4 to the power of 2 plus 2 times 4 to the power of 1 plus 3 times 4 to the power of 0 plus in the right side of the radix we have negative power of 4. So it's 2 times 4 power of negative 1 plus 3 times 4 the power of negative 2 plus 1 times 4 to the power of negative 3. So this one is our number in base 10. If we calculate this number, the final answer in base 10 is 75.703125 in base 10. Okay, now that we have our number in base 10, we can convert it from base 10 to base 5. We know that for converting a real number which has both integer and fraction parts to power up to other bases from base 10, we need to separate the fraction and integer parts and do the conversions, and at the end add the two results. So we need first convert 75 to base 5 and convert 0.703252 to base 5. We know that in order to convert the integer part, so let me just write it here, integer part, and here is fraction part. To convert the integer part, we divide the number by the base. Okay, so 75 divided by 5 is 15, and like a reminder is 0. The remaining is the 0. 15 divided by 5 is 3, and the remaining is 0. And of course, 3 is less than 5. So we collect these numbers in this direction. So we can easily say that 75 in base 10 is 300 in base 5. So this one was for the integer part. Now let's move to the fractional part, the fraction part, and do the conversion. For the fraction part, we know that instead of dividing, we multiply the fraction part by the base. So 0.703125 times 5 is equal to 3.515325. We keep this integer part and multiply the fraction part by the 5. So the result is 2.578125. We keep this integer part and multiply by 5. We will have 2.09090625. We again keep this integer part, multiply the fraction part by 5. The answer is 4.453125. We already know that for converting or for fraction conversion, we might not reach to the exactly conversions, and we have to stop in a point in a job. I lost my connection. Let me see if I can continue. Okay. So we need to stop in a like desired resolution. Here we want to stop at 4-digit resolution, and so the fraction conversion is 0.3224. So we can say 0.703125 in base 10 is equal to 3.3224 in base 5. Now that we got the both conversions, fraction and integer, we can say 75.70323125 in base 10 is equal to 300.3224 in base 5, which is equal to, of course, 1023.231 in base 4. And here we have the answer. Okay. Here I want to talk about like how we can convert 1 digit in base 16 to base 2 or base 10. Let me just show you a number in different bases. So we can say, let's say first one is the binary, decimal, and hexadecimal numbers. For the binary, we start from 0000, and I need to check my computer to make sure that it is recording the lecture. Okay. 0000 is 0 in decimal and 0 in hexadecimal. The next number in the so first let's write the decimals: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0000 is 0. 1 is 0001. 2 is 0010. 3 is 0011. 4 is 0100. 5 is 0101. 6 is 0110. 7 is 0111. 8 is 1000. 9 is 1001. In hexadecimal, up to 9 is the same as decimal. So 5, 6, 7, 8, 9. So let's continue for the next 6 digits for the hexadecimal, which is A, B, C, D, E, F. A in decimal is 10, B in decimal is 11, C in decimal is 12, D in decimal is 13, E in decimal is 14, and F in decimal is 15. 10 in binary is 1, 0, 1, 0. 11 is 1, 0, 1, 1. 12 is 1, 1, 0, 0. 13 is 1, 1, 0, 1. 14 is 1, 1, 1, 0. And finally, 15 is 1, 1, 1, 1. So it's this one is like the entire table, which shows the three most important bases, which is base 2, base 10, and base 16. Okay, so if you look to the first digit of the binary, so you can see that for each number we have like a change in the first bit. So the first bit is changing for each number, so 0, 1, 0, 1, 0, 1. The second bit, every time the first bit is like 1, the second bit is changing. So first bit is 1, so the second bit is changing. In here, the first bit is 1, so the second bit is changing. Here, the first bit is 1, the second bit is changing. Here, the first bit is 1, the second bit is changing from 1 to 0. The same thing for the next digit, third digit. Every time the second digit changes from 1 to 0, the third digit is changing. So at this number, second digit is changing from 1 to 0, so the third digit changed from changed, in fact. So, and also here, if you look, the second digit changed from 1 to 0, so the third digit changed, and so on. And for the fourth digit, again, every time the third digit changes from 1 to 0, the fourth digit changes. So here, and that's it. So this one was the base conversions and a short introduction to base the number systems and base conversions. In the next lecture, I will talk about signed numbers.